Hi everyone, welcome to my channel. My name is Manuel, and today we are going to talk about my Datathon project for the Machine Learning Engineering postgraduate program at FIAP. This project is about predicting academic risk for students supported by an NGO called Magic Steps. The idea was build a machine learning system that identifies students at risk of failing behind in school before it actually happens. Our model achieves 95% recall, which means we catch 95 out every 100 at risk students. So let's get into it. So let me explain the problem we are solving. Magic Steps is an NGO based in São Paulo. They support socially vulnerable students with educational programs. So every year they collect data about each student through a comprehensive educational development survey. um, in the challenges, some students fall behind their ideal academic phase. And if the NGO can identify these students early, they can provide extra support. But if they miss a student, that student may fall further behind with no help. So the cost of missing and at-risk student, it's much higher than the cost of flagging someone who turns out to be fine. That's why we optimize our model for recall. So we want to catch as many at-risk students as possible, even if we occasionally flag some false positives. Our project is composed by three other projects. The model itself, where we have our data set here, our front-end application, and also our infrastructure as code. And if we have all these projects at the same level or build our systems locally with Docker Compose, we just need to enter on our infrastructure as code project and run their Docker Compose up, build. Let me make a demo of each one of our services, beginning with our mobile API. If we access the slash docs, we can see our Swagger with our endpoints listed with samples. Um, and if we run the train endpoint, if we go back to our Docker environment, we can see on the risk model container the logs of the execution and also the experiments generated using MLflow. This is our front-end app where the user can register a new student. Let's put here an example. After registering the student, we can view it and then we can use our model to make an evaluate risk action. So let's try this. and our model gave us the risk regarding these indicators. Talking a little about our ML flow integration, we have this system where we can see our experiments and the run of each model, and also some metrics regarding um, the score, the type of the model, and our experiment name that we are using. On our provisioning environment, we have this ML flow exporter who acts like an agent, exporting what happens inside ML flow and integrate it with our Grafana. And if we access our Grafana, we can see some service health dashboards with prediction metrics, API metrics, and so on, and some dashboards. And one of them, it's our ML flow metrics. And we can see here dashboards with the same information that we get on our ML flow. Making a deep dive on our system architecture, we have here our front-end application, our backend that integrates with our model API, and our ML flow to get all the metrics of our experiments. And going along, here we have our monitoring stack composed by a Prometheus, Grafana, and our alert manager. Here we have our exporter who gets all the experiments metrics and send this to Prometheus so we can see clearly on our Grafana dashboards what is happening and how our training is going. Now, making a deep dive on our modeling approach, we compared three classifiers: the logistic regression, random forest, and gradient boosting. We choose these because they offer different trade-offs. Logistic regression gives us a linear baseline. It's fast and interpretable. Random forest handles no linearity and is robust to outliers. In gradient boost, we use sequential error correction, focusing on the examples previous models got wrong. For each model, we build the full pipeline and ran five-fold stratified cross-validation using recall as the scoring metric. Then we fit on the full training set and evaluate on the held out test set. So logistic regression achieved 37% test recall. Random forest did better at 55%, but gradient boosting reached 95% recall. So it's an 2.5 improvement over random forest. So gradient boosting was the clear winner. The boosting mechanism naturally focuses on misclassified students, the harder cases. With 100 shallow trees, it captures nonlinear interactions between our indicators without overfitting on our samples. Even though gradient boosting doesn't have a native class weight parameter. The recall focused model selection handles effectively our class imbalance. Last but not least, on our academic risk infrastructure as code repository, we have our GitHub actions prepared to deploy all our services and our monitoring stack to an EC2 instance on AWS. For make this work, we just have to configure our access to AWS and run our Terraform here to provision our EC2 instance. And then we can configure here on settings, um, secrets and variables, actions. We can configure our EC2 host and our EC2 SSH key. And with this configured, we can run our actions here and deploy all our stack to the AWS environment. To conclude, our academic risk prediction model is now production ready. We achieve 95% recall, meaning we identified virtually all at-risk students. Our F1 score of 82.9% shows we maintain good precision while optimizing for sensitivity. This system is fully built using Docker. We have Prometheus metrics, evidently drift detection, and structured logging for production monitoring. So that's all for this one. I hope you all enjoy it. I will leave all the links in the description and see you in the next one.